I'm going to speak to you today about 2016 monsoon convection and its place in the large-scale circulation using Doppler radars. So our aims then, well, we use a network of ground weather radars over India to analyze convective storms. Now you might associate radars with nowcasting and forecasting of rainfall. However, we can also use archive radar data to better understand convection. And so our research questions then are, what patterns of convection exist across India in 2016? And how do these convective cell patterns fit within the large-scale circulation? So that is to say, over major timescales of variability, such as the monsoon. So if you're not familiar with your radar, this is our radar dish here, and it's emitting this electromagnetic pulse, which is going to intercept this cloud, or perhaps a sheet with a parachute. And this cloud is full of lots of cloud droplets or raindrops. And this is going to scatter this electromagnetic pulse in various directions, but some of it is going to be received back by the radar dish. Now, the amount received back by the radar dish is a function of the number and, even more importantly, the diameter of these particles. So if there are a lot of very large raindrops within this cloud region, then we're going to have a high Z, which is our reflectivity. Now, reflectivity is how we are going to analyze convective storms. And the monsoon then, it impacts over 1 billion people. It's a highly complex phenomenon with significant interannual variability, but it's also difficult to predict. And this is partly due to a lack of historical observations of convection, which brings much of the monsoon rainfall. So this is our map of Indian Doppler radars. There's 17 of them. And we see that there's these 100-kilometer range rings around each radar, which is the distance at which we are satisfied we can robustly monitor convection at. And on the right here is our climatology of convection during the June, July, August period. You can see there's these strong westerly winds bringing in moisture from the Indian Ocean and bringing lots of rainfall to this western coast region in particular over India. So what we do with these reflectivity values that I just discussed is we construct a 3D grid of reflectivity from each radar. And this allows us to extract convective regions which are bounded by this black contours here for this particular example, which gives us information on storm size and intensity based on the reflectivity values, and also storm height, which is basically how high do those reflectivity values go in each storm. So how deep are the storms? So then if we take these convective cells over the entire season for a particular radar site, such as Agartala in northeastern India, and we take these convective cells for each half-hour period local time, then we can see that there's a maximum in the number of convective cells in the early afternoon over Agartala. And interestingly, there's more deeper cells over the nighttime period, even though there's less cells overall. But these deeper cells do seem to contribute more in the way of rainfall, as observed by GPMI merge rainfall, shown by this blue line. So I hope you found that interesting. That's what we're able to look at with radars.